Okay, so today we're going to look at laws of logarithms. We're going to expand and condense logarithms. You know, condense means like make a single log, and expand means make a bunch of little logs. Fortunately, there's no log cabins or anything. It's just math still. But we have three of these properties. Okay, is that this is log base A. These are all log base A's, correct? So any of these properties you use, the base of the logs never change. And if you see two logs with different bases, you probably can't do anything with them. It's just kind of a headache. But what this says is, and again, I use little a and then capital A. They're completely different letters. I wouldn't have chosen it, but it's what's on our formula sheet. So if you have the log base A of A times B, this is a product, correct? Two things multiplied together. It could be 3 times X or whatever, A times B. And that'll equal the log base A of A plus the log base A of B. So you expanded it, but you took that was multiplication inside a single logarithm, and you made it as the sum of two logs. Now originally, when people first used logarithms, like, I don't know, 500 years ago, it was a way to deal with really, really large numbers. So instead of having to multiply two large numbers together, you could take two different numbers and add them. It's much easier to add things by hand than it is to multiply. The second property is the quotient property. If you have a quotient inside the logarithm, so, you know, A divided by B or whatever, 2 divided by X, that becomes the log base A of the numerator minus log base B of the denominator. So again, instead of division inside, it's subtraction. The last one, which we use a ton when we solve, if you have a log base A of some argument A raised to the C power, so if you have an exponent inside your logarithm in the argument, it says you can take that number and you can move it out front as a multiple. So instead of taking a really large power, you could multiply. That's a big time saver traditionally. Now we don't really use them for that anymore because we have calculators. So on our paper here, let me just run through a few examples, and then like I said, the rest of these, we'll get them out Friday after the quiz, and we'll work on them, and we'll use them for next week. So for number 1, we have the log base 4 of 2 plus the log base 4 of 32. Now both of these you could find the log base 4 of 2. It's actually 1/2, right? Because it's 4 to the 1/2 power. But let's use our new properties here. These are both logs base 4, correct? And so if I combine them, you're going this way, right? So instead of saying log base 4 of 2 plus log base 4 of 32, we could say that's the log base 4 of 2 times 32, which we all hopefully know is 64, right? Now, 4 to what power is 64? 3. So this answer would be 3. Right. Now, if you did these each individually, I think you'd get 1/2 plus 2.5. But this is easier, right, to get the bigger number. Is everyone doing okay with that? Yep. So we can use these laws to evaluate sometimes. Let's goof with, let's look at the third one here because it looks important. We have -1/3 log. Oh, there's no base on that logarithm. What's that mean?
10.
Yeah, it's base 10. It's common log, right? Very good. So now, if I want to condense this, I want to get this number out in front, not there anymore. Well, we know if there's a number multiplied by the log, we can bring it in as a exponent. So this gives us the log, common log of 8 to the -1/3 power, which is a little bit weird, right? We got to deal with that. Now, to get rid of a negative exponent, you move the base to the denominator, correct? So we could say this is the common log of 1 over 8 to the 1/3 power. What is 8 to the 1/3 power? It's 2, right? It's a cube root? Yeah, very good. So this would still be the common log, but it would be the common log of 1/2 is how we could simplify that. Are we doing okay there? Again, the log didn't go anywhere, right? We never evaluated anything. Like 10 to what power is 1/2? I have no idea. Doesn't simplify nicely. These are, again, just ways to kind of manipulate things and move them about using these properties. The next thing we're asked to do is to expand. Let's do a tough one here. Look at a couple of these. So we have, for number 4 on your paper, we have the log base 2 of 6x. This is a single logarithm, but we see there is a product inside there, correct? So we write as the sum of 2 logs. So log base 2 of 6 plus log base 2 of x. It's expanded. Now, I don't know what you're going to do with it, but that's the process to expand it. Let's grab number 6 here. Maybe take a second and try this one. It's the natural log of AB over the cube root of C. So maybe try 5 and 6 on your paper there, and we'll take a look. Okay, so for number 6 here, we have, again, we know this is, what's this called? Natural log. What's its base? E. E is just a number, right? It's a weird one. Just a number. So, the first thing we want to address, it would be wrong now to address like the cube root. We're going to address it later, but the cube root doesn't hit everything inside there, right? It only hits part of it. So let's look at this. We got a fraction bar. We obviously have a fraction. So let's use this second property to expand that to be the natural log of AB minus the natural log of the cube root of C. Does that work for everybody there? So now at this point, is this still a product in here? Sure is. So we could say natural log of A plus natural log of B. Here, what we'll want to do to expand this is we want to rewrite the cube root of C as a 1/3 power. Right? So it's the first thing we did in this semester was do exponents, right? Now we're still talking about exponents. The semester's almost over. So what can I do with the power here? Put it out in front. So we get natural log of A plus natural log of B minus 1/3 natural log of C. That's what we'll end up with there. Does that seem believable? Something to be careful about is it didn't happen here, but you notice how we had the natural log of AB and we made 2 new logs? If there would have been, say, a negative out in front of this one, or a number out in front of it, it would have had to go to both these places. It would get like distributed. Does that make sense? So if you have something that's negative and you split it into 2 things, it makes both of them negative. So that's that. And then let's look at where we condense, which, condense is going that way, expand is going that way in terms of our formulas. So here we have, so this is number 7, 3 times the common log of x plus 1/2 common log x plus 1. Something to be careful about here. I know that we're condensing, but even if we were expanding, there's no rule that says if you have 2 things added together inside a log, there's no rule for that. So we can't. That's not a thing. So for this, before I put them together, as we look at these laws, notice this is a log plus a log. There's no numbers in front of it, right? Either of them. This is a log minus a log. There's no numbers in front of it. So before we can do either one of these top 2 properties, we have to deal with the numbers out in front of it. That's what third property is for. So it's going to become the common log of x cubed, yeah, and then plus the common log of x plus 1 to the 1/2. And actually, what's a 1/2 power the same as? Square root, right? So we could do it. We could combine them. If you had the common log of x cubed, x plus 1 to the 1/2, that's great. Oh, I need a bracket though. That's fine. You also might write it using a square root. You might see it written as the common log of x cubed times the square root of x plus 1. If that makes sense. Right, again, 1/2 power, I just rewrote it under a square root, just to kind of give you an idea there. Now, none of those can be combined or anything. It's just x cubed times the square root of x plus 1. Okay, so to wrap up today, we want to talk about what's called the change of base formula. This is especially important if your calculator doesn't have a button where it allows you to change the base. Now, if it does, and you want to graph like log base 3 of x, you just go to y equals, you type the log and you type the 3 and then you put the x and it does it for you. You're all set. You could go to a table or you could plug in x values and find y. It's a nice way to explore it. Otherwise, though, and traditionally, if you have a log base b of x, right, so just some logarithm, the base is b. It could be whatever you want it to be. But you can rewrite that as the log base a of x divided by the log base a of b. So it's just important to see where all these numbers go. You picked a new base, correct? Like you could pick whatever you want. Normally you choose 10 and use a common log, or you choose e and use a natural log. But you could use anything. You could use log base 7.2 if you wanted to. It would still work. So you get to pick a new base. Whatever the argument was on the original logarithm is now the argument of the numerator. And whatever the old base was, you take the log base a of that old base. So the base becomes the argument of the denominator there. So, for example here, number 9, we have the log base 8 of 5. I know most of you can type it in your calculators, which is awesome, but let's pretend we don't have that button and we're just going to use a natural log or a common log. So what I mentioned here is normally we use a equals 10 or a equals e, because those are the two buttons we have, right? When a equals 10, it's a common log, and when a equals e, it's a natural log. So if we wanted to evaluate this and get a decimal expansion for it, what we would do is we have two options, and they're both going to give us the same answer. You could either do the common log of 5 divided by the common log of 8, or you could do the natural log of 5 divided by the natural log of 8. Test it on your calculator. They're both going to give you the same decimal expansion. The one thing you do want to be careful about is make sure you close the parenthesis, right, around the 5, because if you don't, it might think that you're taking the log of a log, and it could get messy. And notice this is not the quotient rule, correct, from earlier today. That was a single log with a fraction in it. This is a fraction made up of two logarithms. So as we do this one, I'm going to type that in and see what we get. Should have written that down, I guess. We'll do 8 divided by 5. Oh, I did it backwards. Divided by natural log of 8. And we get, let's say, 5 decimal places. So you get about 0.77398. Did we get that? Yeah? Now, how do you remember where the base goes when you do this process? To the basement. Where else would you put a base? Yeah? Yeah? Oh, I know, it's painful.
I like that one.
You like that one, thank you. So, does that make sense though? That's the change of base formula. So say that you're studying tonight for your graphing test and you're like, I want to check this graph on my calculator. So say you're graphing, f of x equals the log base 5 of x plus 2 minus 3. Right? So we know how to do this, correct? We do our parent function, we'd move it 2 units to the left, we'd move it 3 units down, and we'd have a great time with that. But if I wanted to type into my calculator to check my work, not that you could use a calculator to graph with my hand, you would type in y equals, I'm going to go ahead and say the common log of x plus 2, people seem to like that one better, divided by the common log of 5, and then minus 3. That'll give you that graph there. You just have to use the change in base formula there to do that. So it's just something neat to experiment with. Questions?
Is the -3 like out of the?
It's outside of the logarithm. Yeah, here's the log, and this is like the whole function. You're subtracting 3, so that's going to be a down 3 shift. Okay. So there we go.